Hello, class. I am going to start the second lecture today. It might be the last lecture because I saw it's not going to rain. It's been trying to rain all day, but this is really the second in a series of what I would consider to be 5 very interesting and important lectures. The first one being how propagation delay enters into the electromagnetic wave, changing with time and with distance along the path of propagation. So that was good. Now, what I want to do today is now we've really learned the exponential form. I think you've worked with the exponential. I'm hopeful that you've worked with the exponential form prior to me introducing it. Maybe seen it in other things. I'm sure, I'm assuming that you have, but I'm going to go back. I want to look at something today and just do a derivation. It's going to come back at us later on, and it really isn't totally, it has something to do with the telegrapher's equations that we're going to go into. It's sort of like a warmer upper, what would you call it, practice for us going through the telegrapher's equations a little bit later on. But what I want to do is I want to look at an RC circuit, right? And the transient and filtering characteristics of that circuit. And I want to do it in a way that we analyze it like, graduate engineers really would analyze a circuit like that. That pen's no good. Oh, that's the old pen. How did I get that one? So that's what we're going to do today. What we're really looking at today is an RL circuit response. All right. And let me run my line down there. I always forget that last line, don't I? So and this is probably how you learned it. I want to show you how I use all of this math, and we're putting all this math together. I don't want to just introduce it and then say, okay, yeah, you're going to be using that grad school, but not show you what to do, and we're going to use a lot of it. So let's start at the very beginning. I may need 2 sheets of paper even to do this, but let's say that my time domain form of the equation for the voltage is going to be V max. Yes, that M stands for maximum. It's just the peak voltage, if you want to think of it that way, times the cosine of omega t plus phi, right? Whatever it is. I'm saying it could be 0. Phi could be 0. Phi could be 180. Phi could be 72. I don't know what it is. It doesn't matter what it is because I'm just writing out this relationship for an RL circuit and how that circuit responds, right, to waveforms of different frequencies passing through that circuit. And this is how it responds. It responds R times I, and of course the current is a function of time, right, because it's going to be changing. Plus L, the inductance that I've got there, times di of t with relation to dt. Right, so many of you have probably seen that equation and worked with that equation. I'm hopeful that maybe you saw it and you worked through it in network theory 2, or maybe definitely in analog circuit design. I would think so, because filters, I mean, RL filters all use this relationship. So having said that, and happy that that's probably what you've got, who knows. But I do want to express, like we expressed V up here, right? V max times the cosine of omega t plus phi. Well, I want to do the same for I of t, right? And I of t is going to be I max, just like V max. I've got I max times the cosine, and I'm going to say that this is omega t plus theta. right? Not phi. We don't have the same phase shift for the current as we do for the thing. And of course, that would be relatively true, because remember, V equals IZ, right? V equals IZ. So depending upon what the impedance is, that's going to mean that the voltage and the current are phase shifted from one another, isn't it? So we don't know what that is. I'm just saying I'm going to call this one phi, and I'm going to call that one theta, just to denote that they are not the same phase shift. They're the same frequency, but they're not necessarily the same phase shift. Okay, does everybody see that? You stupid little camera, get back. Back. Come on, camera. Ooh. Oh, there you go. Oh, okay. Oh, that. Excellent. All right, now let's get on with it. As you can see, and of course I wanted to point out, let's rewrite this equation now. But let's take into account these. Now, how can I rewrite this in its exponential form, right? Let's rewrite the whole equation that I've got here in its exponential form. So I'm going to say that this is the real, we'll do them one at a time. This is the real of V max times E to the j omega t times E to the j phi. All right, I'm going to stop there for just a second and say, does everyone see why I did that? Does everyone see why I've got V max? Why do I have real? Because it's a cosine. Why do I have V max? Because V max is in the statement. Why do I have E to the j omega t? Because really I have E to the j omega t plus phi, but I can break those up just like anything. For instance, if I had something that was, and this is just go back, 10 to the 6, well, isn't that equal to 10 to the 2 times 10 to the 4? Isn't that how that works? 10 to the 2 times 10 to the 4 equals 10 to the 6? Yes. So that's all I've done here is I've just broken those two up because I can. All right, well, let's do the other side of the equation now. Now I've got R. And what is R going to be multiplied by? Well, it's going to be multiplied by I of t. Well, what have I got here? Well, I've got the real, right? Because it says cosine. I've got the real part of I max, right? And then E to the j omega t, E to the j theta, right? Does everyone see that? So that's what R is. So R and then times I. Now, what is di dt? If that's I, if this is I right here, what is di dt? You know, I should probably write this I, or why don't I write this I up here in its form so everybody can sort of see it, and that's going to be the real part of I max E to the j omega t E to the j theta. That's sort of written in there a little, and of course my thing is now not working anymore. There we go. Yeah, I'm going to double check that again, and but every time I go back, you know, the settings that I set it on are still there, and maybe it's a light thing. Maybe I don't have enough light. You know what? Usually it's so bright because of the sunlight. Maybe I could just open these up a little bit. Maybe that would help. No, because now I can see all the birds, and I'm not going to be able to teach anything. Okay, I'll pull it down a little bit. So I've got the light on here. I guess I need like another light to just blast down on there. So let's go di dt. Now, you know what? That doesn't give me enough room. I'm going to just write it down. No, I guess I could. di dt. Let's look at this one right here. This, by the way, the real I max e to the j omega t e to the j theta is the same thing I have written up here. You just can't see it because I thought I had enough room, but I didn't. All right, so let's go to the derivative with respect to t, and that would be equal to the real I max, right? E to the j omega t e to the j theta, and then what else would we have, right? Wouldn't we have j omega? Now, why did I put j omega? I'll put parentheses around that. Why did I put j omega in there? Because isn't the derivative of e to the j omega t? Yeah, let's do that. So the derivative with respect to t of e to the j omega t equals e to the j omega t times, right, times the derivative of the argument to Euler's constant, right? So e to the j omega t times, and what's the derivative of j omega t with respect to t? That would just be j omega. Does everyone see why I put the j omega there now? If I'm sure that you did in the beginning, and I just, beating that to death. But that's why I got the j omega there, and that's where I'm going to use, because I've got to use that plus L now times di dt, which is going to be equal to the real part of I max. I want everybody to remember that I sub m, let's just I sub m equals I max, right? Not imaginary. We're not talking about imaginary here yet. It's just I maximum. I could put I peak or whatever, but I use V maximum. So I wanted to use I maximum. I just want to point that out several times as I go along here so that you'll know. So I maximum times j omega times e to the j omega t times e to the j theta, right? Okay, so there we go. So we've got all of that in there. Now you're probably saying, hey, how could we simplify this? Is there a way that I could take these two, because it's really the real r times this and the real and everything else? Is there a way that I could actually put all of those things together, because they're common, right? What do I have in common between this product here and this product here? Well, obviously R and L aren't common, are they? But what is common is going to be all the rest of this stuff. So let's write that down there. I'm going to put a line across here, right? We're still going to be continuing on, but what I'm going to actually probably write it in a different form now, because I want to look at what is the same. The I maximum is the same. E to the j omega t is the same. E to the j theta is the same. The only thing that is different is going to be my j omega, which I've got in there, and I think everybody can see that e to the j omega, or yeah, e to the j omega t are both the same in here too. So what I want to do is I want to pull these out, and I'm going to bring them together, and I'm going to say I want the real on this side I'm going to be working with this side over here, of r, well, actually, let's pull e to the j omega t out of there, right? If we pull that out of there, what that leaves me with is r times I, maybe I should just not put the down there anymore, times e to the j theta, right? That's that. Do I have anything else in there? No, no, I don't. R, right, times I times e to the j omega. Now you're probably saying, can you bring the r back inside the real? Absolutely. Absolutely. No problems with that at all. R is just a constant, isn't it? So I can easily bring that back inside the reel. And that's why I'm going through this, is really to show you how, how to use the things and what the operations are. Sometimes I might just do things and not remember to tell you what operation I actually used, what identity, but hey, you can't stop me. So RI e to the j theta, and that's because I took e to the j omega t out of there. Now, what does that also leave me, right? Plus, what have I got out here? Well, I've taken e to the j omega t out of the system already, haven't I? So that leaves me with j omega, L, and I, and e to the j thing. So that's what I get. So I get j omega, L, I, right? Does everyone see how I've taken all those? And then e to the j theta. And you might say, hey, why don't you take that e to the j theta out of there? Hey, don't worry about it. Don't ask me questions. I'm just doing it this way. Just be happy. Everything's working out just fine, right? Now that is going to equal the other side, and that's this side over here, right? The real of v max. I'm just going to use v. Of v e to the j omega t e to the j phi. So basically the same thing that that we've got there, right? Okay. Now we are going to look at this equation. So here's my boundary conditions. My boundary conditions are at t equals 0, omega t equals 0, right? And that would be 0 radians, wouldn't it? So at t equals 0, omega t equals 0, and I know that because anything times 0 equals 0. Now, I also want to look at when omega t equals 90 degrees, which in radians we know is pi over 2, right? So those are the two different things I want to look at, and I want to see what happens. How does this equation of state that I've got here collapse when I put in omega t equals 0, right? That's the first thing that I want to do. And you can see that I've got reals on both sides now, right? And of course, that's real equals real. So I'm just going to compare really what's inside there. So the first thing is omega t equals 0. Well, let's take this. So that would be the real. And then omega t equals 0. So that'd be e to the 0. What is e to the 0? E to the 0 is 1. Oh, I got e to the 0, or anything to the 0 equals 1, doesn't it? So e to the 0 equals 1. So this tells me that for that condition, now let me write it. Omega t equals 0. That's this condition right here. I put a line underneath it. I'm going to get the real of R I E, oops, I'm sorry, e to the j theta plus j omega Li e to the j theta. And that equals the real of V e to the j theta. Oh, phi. That's a phi. I know it doesn't really look like a phi, but it's a phi. I'll make the top. Oh, yeah, there you go. It's a phi. Believe me. So at omega t equals 0, this is what we've got. Right? That's my equation when omega t equals 0. And of course, that would be 0 radians. Oh, wait, no. Yeah, 0 radians because omega radians per second, t seconds, so cancel each other out. Okay, so that's one equation that we have at omega t equals 0. Let's just sort of extend this so I could box that in. That's my equation for omega t equals 0 radians. Let's look at another one for omega t equals 1 equals pi over 2. And pi over 2 is 90 degrees, of course, right? And on the complex plane, let me just draw this complex plane here. Now, didn't I say omega t equals, so this is for omega t equals pi over 2 radians. Okay. Now let's just look at that. E to the j omega t. And omega t is pi over 2 now. So it's really e to the j pi over 2. E to the j pi over 2 is equal to the cosine of pi over 2 plus j times the sine of pi over 2. Excuse me. Obviously, my COVID coming in to kill me. Now, let's think about pi over 2. Pi over 2 is 90 degrees, right? So the cosine of pi over 2 is going to be 0. And the sine of pi over 2 is 1. 1 times j is j. So e to the j pi over 2 equals j, doesn't it? Does everyone see that? J times 1, 0 plus j times 1 just gives me j. So the way that I could write this equation again, and remember, let's go back to our general equation that I had here. Right, here's my general equation. I'm just going to circle that. And then here's my equation when omega t equals 0. Here's my equation when omega t equals 1/2. It's going to be the real part of j, right? Because in e to the j omega t equals j times r I e to the j theta plus j omega L I e to the j theta, right? Equals, and let's do the same thing on the other side because I've got e to the j omega t here and I know that's j. So this is the real part, right, of v, and then e to the j omega t just equals j. I should put the j out in front, I suppose. J times v times e to the j phi. Does everyone see how that works? And now I want to point something out to you too, because I'm going to use it right here. is that the real part of of j times a complex number equals minus the imaginary part of that complex number. I know you're saying, I can hardly read that, let alone you got a Cartesian coordinate in there. That's right. So the real part of any complex number preceded by j equals the negative of the imaginary of that complex number without the j in front. Right? So that's an identity that you know, and you can use it yourself too. Just take the real, just take the real of 3 plus j4, and that gives you 3, doesn't it? Right? Oh, I'm sorry, I got to throw a j in front. Well, I got to throw a j in front of there. J, there you go. So the real of j times 3 plus j4 would be j3 plus minus 4. So it'd be minus 4 plus j3, right? So minus 4 plus j3. And so that's what I want to point out. The real of that is going to be minus 4, isn't it? But if I was to take the imaginary part of 3 plus j4, that would just be 4. So you can see where the minus comes in. I'm sure everybody understands that. So that's what I'm going to apply right here. I'm going to say that this is the same as the minus the imaginary part of r I e to the j theta plus j omega L I e to the j theta, right? And what that's going to equal is it's going to equal minus the imaginary part. On the other side, I'm doing the same thing, right? That should probably be a brace. Anyway, and that is just going to be minus the imaginary part of VE to the J phi. Okay? Now, the imaginary, you can see this is minus imaginary. So those both are going to just cancel out the minuses there, right? But what we can see is that whether we're comparing this, so I'll just make those pluses. Whether we're comparing this or whether we're comparing this right here or right here, you know, we can say RIe to the j theta plus j omega Li e to the j theta equals the real of VE to the j phi. Does everybody see that? So let me just no, that's right. Yeah. Okay. So I get RI. I'll write it all out. E to the j theta plus j omega Li e to the j theta equals V e to the j phi. All right. Yeah, that's good. All right, now I want to take out of this side of the equation I e to the j theta. So if I take I e to the j theta out of that side of, oops, excuse me, no, I don't want to do that. Take it out of that side of the equation. Sorry about that. Didn't want an equal sign there. Then what that leaves me inside is R plus J omega L, right, equals V e to the J phi. And so when we look at the maximums now, we've got a maximum here. I mean, I took the m's off there, but if we look at the ratio of the two of those, V max to I max, what that gives us is R plus J omega L. Okay? You're probably thinking, oh, well, what are we ever going to use that for? You're going to use it in the next lecture because I'm going to start to derive the telegrapher's equations. And if when you're looking at this and what I did here in that derivation, you're saying, that was so easy. I don't even know why he screwed up on that couple little parts there because this is so easy. And it is. And it becomes so easy. And it's like second nature. And you learn little identities like this that you will carry along with you. And I'm sure that a lot of people who are even in college right now, even in your program, haven't seen this yet. So, you know, this is where you're going. This is how you're going to do all of what you're doing in the future, I hope. You know, when and wherever you're working on those phased array radar systems for our defense or fiber optic transmission or whatever, you're going to be working on a lot of it. Okay, do I have time? Oh no, it's we're just about right there. So that's just a little bit of what we're going to start doing too. So this is the second, let's say the second lecture, like I say, 5 or 6 lecture series when we're going to start talking about attenuation and transmission in metallic conductors, and the attenuation of that, and all of the things that go into that. Okay.